All right. So A. All right. So this is well, first let's look at the forward pass. The forward function. We start with x, pass to ff1, hd, ff2, hd, ff3, y. Right, so you're going to use ff1, ff2, ff3. This one is not used. So it's there just to trick you guys. So ignore that for now. So ff1 takes in 25, output 100. Right, so this one, A needs to be 100 to take in this and output 200, 200, 200. Right. How many hidden layers are there? So it's only 1 and 2 because the third one is the output layer. 2. What is the size of the output tensor? So the output is 200. Right. So it's 32 by 200. How many neurons does FF3 have? So this one has 200 neurons. How many parameters that FF1 has? So it's 100 neurons. Each of them has 75 inputs plus bias. So it's 7600. All right. Okay, so a quick recap of last time. Right. So last time we talked about fully connected networks, which is our function, right? Our function can consist of the neuron, which is this thing, right? And nonlinearity, which is some nonlinear function, right? For example, the Ley rule, right? Ley rule or tan H or sigmoid, right? Then we also have the softmax layer, which is turns the model into like probabilities. And to train the model, we have laws, right? One is MSE, the other one is Gaussian. This one is for classification, right? And MSE is for regression. And if we just train using this kind of losses, we might run into overfitting problem, right? Which we need to reduce overfitting by like doing regularization, either by dropout or by controlling the learning rate by scheduling. So that's like an overview of last time. So today, right? Today we're going to talk about two pieces of neural network beyond just a typical neuron. So first one is convolution neural network, which is typically used for images. So this is like so this is in 2D, right? 2D images, and we have what we call a convolution layer and a subsampling layer. So we will repeat these two over the course of the network and end with like a fully connected layer or like the layers that we learned last time, right? So usually we consider the first part as like a feature extraction model, and then the later part as a classification model. So these things extract some features that is feed into the classification layer later on. And the output of the convolution layers we usually call feature maps. Right? So these are the name of the output. So why do people use like convolution? Right? The motivation of convolution layers are we are extracting hierarchy of representation. So we're going to start with like simple things like pixels that is used to learn edges in the image, and then learn like parts of the face, and then output the face of the person. Right. So we learning progressively more abstract pieces of information. Right. So that's the idea of like why do we stack the layers? So each of this extraction will like, okay, this first is like the lines, the face, the face parts, and then the face later on. All right, so what's the ingredient of convolution neural network? So we're going to talk about the first piece, which is convolution filters. So let's say I have an image. This is a 100 by 100 pixel image. I have a filter, or sometimes people call it kernel. So I have this, right? You can treat this as a neuron, right? You can think of this as a neuron, but instead of like a typical neuron that you just multiply and sum once, right? This neuron is going to be used in a convolution kind of technique. That is, okay, you're going to put the filter on top of the input. Right. So the filter will have its own weights. So this is the filter weights. And these are the inputs. Right. And then you're going to multiply point by point and sum them all up, get a number, and this number will become your output. Then we're going to move the filter by 1 pixel, or we call it a stride of 1. We move it 1 by 1 pixel. Notice the weights are the same. The weights are the same, but the input changes. And we do the calculation again, right? We get another number. We move it again. We move it again. Get another number. Move it again. Get another number until you finish, right? You move until the end. Right? You move until the end. And you get some outputs here. So you're going to have like 98 numbers at the top level here, because you can move it 98 times, right? You can move 98 times. And once you hit this endpoint, right, you're going to just start over on the next line, right? So you're going to move the next line and then do this and then keep filling, and then start over, keep filling, start over, keep filling. So you're going to get 98 by 98 output for one filter. So this is like the calculation is very similar to convolution. I think you guys learn convolution. Yes, right. The only difference is in convolution, in signal processing, the convolution is flipped. This one, there's no flipping. You just slide. because the weights here are all learnable. So since you are learning the numbers anyway, there's no point in flipping, because if you flip, you just learn the mirror of the image. All right, so since you're learning it, whether you're flipping it or not, doesn't matter. So that's one filter, right? If you have multiple filter, let's say, oh, you have filter number 2, right? Filter number 2 get placed here, and you do the calculation, right? It gets moved around. You're going to compute the numbers, right? Another filter is done, right? And let's say you have 3 filters, you're going to have 3 output. Right, so output here will, the number of outputs here, we call it the channel. There are one piece here is called one channel. So in here we have 3 filters. We're going to have 3 channels as our output. This is the first piece, which is called convolution. The next piece, which also is used in the convolution neural networks, is called the pooling or subsampling. So the pooling is, you have a filter again, but there's no computation here in the filter. The filter just look at the input and pick the max. So the max is 9. So you output the max here, and you're going to stride, right? So in this case, we're going to stride by 3. So we move by 3 points and find the max. The max is here. Let's put it here. And so we're going to do this stride until the end, right? The same as before. This layer is called pooling or subsampling, because usually in this layer, you're going to have a stride larger than 1. So your output will become a lot smaller than before. And besides just using the max, some people can use like the average. It's called average pooling. If you use the max, it's called max pooling. If you use like a global max, that is like, oh, you look at an entire piece and find one max. We call it global average pooling. So there are many variants of this layer. So let's do a quick like mental math on what's the output size of a layer. So let's say that we have 4x4 input, and we have a 3x3 filter, right? And now we're going to have padding. That means, oh, in this input 4x4, I'm going to pad 1 pixel everywhere. So it becomes 6x6. Right? And these numbers, sometimes we just pad it by zeros. Sometimes we might pad it with, let's say, like we have some numbers here. We just copy the numbers that is closest. Right? That's another way to pad. But most of the time, people just pad by 0 or like use the same number. Right? Doesn't matter much. But this is padding, right? And we have a stride of 1, right? What is our output size? So let's try this. So, okay, the first one right here, we move 1 pixel here, right? And we move another pixel, it's here, right? We move another pixel, it's here. The last one, this is not allowed, right? The green is not allowed. So we have a 4x4 output out. And since we have 5 filters, we're going to have 5 channels as the output. Right, so that's one example. Let's do another one. Now I have a stride of 2. What will be my output? So this is the first one, right? First output. I move 2 pixel. It's here, right? I move another 2 pixel. Nope, not possible. Right. So we get a 2x2 output as the filter. Last one. So now we have a color image. That is, oh, our input has 3 channels. And the same everything, right? 5 filter, 3x3 filter, stride of 2, pad 1, 5 filters. So there's a convention in convolution layers, that is, the filter expands to be the same number of channels as input channel. So even though I say it's a 3x3 filter, this filter is actually a 3x3x3. So it's this filtering is one filter, right? One filter that is 3 of them together. And when you compute, right, they will have like some weights, right? They will have some weights, and you just multiply all the weights and then add them all together, to get one output. And everything is the same, and the rest is the same. Like, oh, okay, you have a stride of 2, so you're going to move it here, move it here, move it here for the second one, and then you cannot move anymore, right? So the output will be 2x2x5. Another layer that is used quite often in convolution neural networks is batch norm. So let's look at an example instead of reading this. So let's say that, oh, okay, I have an image. So this is one image, right? One input. But actually in my training of the neural network, I may have multiple image. So let's say that, oh, this is 2 input, 3 input. Let's say my batch equals 3. Okay. So all of this is compute at the same time, right? So I feed in to a CNN. And my number of filter is 5. My number of filter equals 5. So my output, I will have 5 channel for the first one. I will have 5 channel for the second one and 5 channel for the last one. Right. So this is my output of the convolution. So, and I want to do batch norm, my batch norm. So one thing that will happen in the neural network is that each of this, right? Each channel is an output of a filter, right? So this is output of filter 1, right? This is output of filter 2, right? So each channel is an output of a filter, right? And different filters might have like different scaling, right? Maybe filter 1 has a very large scale that is like, oh, the output is like maybe 5, 3, or 2, right? And filter 2, right? Filter 1 is like maybe, oh, 5, this one is 3, this one is 2, right? Filter 2 maybe it's like, oh, 0.2, this is 0.1, this is negative 0.5, right? So different filters will have like different scaling because it's a different set of computation, right? So when you have different scales in the input, what happens? Your learning, right? Your gradient descent might be difficult because you will need different learning rate for each of these numbers. But that's not possible, right? That's not possible. So what do we do when we have like some input data that are of different scales? We try to normalize it, right? We try to normalize it. So let's normalize these numbers to be the same scale. So what I'm going to do is, okay, let's use these numbers, compute a mean. Let's say the mean is 4. Compute a standard deviation. Let's say 2, maybe. So I'm going to change this into like, okay, let's standardize all this according to the mean and standard deviation, right? And the different channel has a different mean, right? Maybe this one is 0.1 and the variance is also 0.1. So I'm going to scale it accordingly as well. Right. So this mean and variance computation is done across the values in the mini batch for each filter. Right? For each filter, you compute one mean, you compute one variance, and then you're going to normalize it. So that's batch norm, right? So that's batch norm. I'll just leave it here for briefly. So you can copy, but that's the idea, right? Compute a mean and the variance. But so this is like the equation, right? You have an input here that, okay, let's scale it with the mean and variance. to get a normalized version, right? But instead of just normalizing, right, we can scale it to some number, right? So these two are learnable weights. So there are parameters that is inside batch norm. So instead of just scaling to standard Gaussian, you're going to scale it out, right? Scale it up to some alpha and add some bias, right? Whatever the model choose to pick, right? As they try to minimize the loss. So this technique, right, leads to faster training because now all your numbers are in the same range, right? So it's easier to train, and it's also makes your model less overfitting, right? So there's like two benefits to batch norm. So this is like a visualization of what we just done. So you can think of like the data as different sample, like data 1, data 2, data 3, and different channel and spatial information that is like, oh, the height and width of the image, right? Is this direction. The y direction is height and width. Batch norm try to find the mean for each slice, right? Find the mean of each slice here. This technique of like finding the mean and variance, actually there are many ways you can do this. So this slice, maybe you can do it like this, like, oh, what if I slice like this? What if I slice it like this? Right? There are many ways to slice it. And each of them is called slightly differently. Nowadays, people prefer batch norm for convolution model, and layer norm is for transformer model, which is something that we'll talk about in this lecture as well. Another important concept that you need to know when you discuss like convolution neural networks is what we call the receptive field. So let's say that I have this input, right? My input is 7 by 7, and I have a 3 by 3 filter, right? So this 3 by 3 filter will output one number here, right? So this 3 by 3 is this number, right? This number. I move it 1 pixel, I get another number. I move it 1 pixel, I get another number. Move it again, get another number. The last one is here, right? So I get my output, right, which is 5 by 5, right? So this first filter here has a size of 3 by 3, and it sees the output of 3 by 3. But if we look at the second layer, right, we have the same 3 by 3. What happens, right? So this 3 by 3, right? This 3 by 3, where is this red? red pixel from here, right? From here. Right, from here. So this 3 by 3 on this second layer, see a 5 by 5. Right, see a 5 by 5 in the original input. Right, it sees a 5 by 5 in the input. So this is a concept called global receptive field. That is, how large does the filter see in the original image? Right, so this is global receptive field, right, which is different from local receptive field. That is, in this layer, how large is it seeing? Right, it's the same size of filter is the same. But if you think about the global, you have to look back into the model. Right, so and usually when people refer to just like receptive field, people mean like the global version. So why is this important, right? Why is this important? It's always good to know like how large is your receptive field, because let's say that I want to make I don't know, cat classifier, right? Cat classifier, and this image is 200 by 200. Right? I might need to think about, if I want to do a cat classifier, how large does my filter has to look? Right? Maybe this cat, right, this is like 50 by 50. So okay, if I build a convolution neural network, it needs to be at least 50 by 50, right? Otherwise, it won't see the entire face of the cat. Right? So always be sure that your model has a large enough receptive field for your task. And to give you some sense of like what the filters are learning. So this is an example of like, so this square here is a one filter in the first layer. And it's after it learns from the data, right? So usually in the first layer, the model, the filter will learn simple things like lines, and layer 2, you start learning more sophisticated things, like some, I don't know, it looks like a coronavirus or something. And in layer 3, you start seeing things like, there's a car, a wheel of the car. In layer 4, like, there's like a chicken, maybe chicken leg here. Right, so the filter pretty much like learns like important patterns that you need to look for in the data, right? And the higher layers will look for larger patterns. Why does it look for larger patterns? Because this one has higher receptive field. Right? As you stack layers higher and higher, the higher layers will have larger receptive field. So it will look for larger patterns. So that's it for convolution neural networks. Right? You're going to have some convolution that output feature maps. We call it feature maps because it will look for patterns and it will create like a mapping of where you see those patterns in the image. And then you do subsampling, that is, oh, okay, your image becomes smaller, and then you do convolution and subsampling, the image becomes smaller, and then a fully connected layers. Right, so that's an overview of convolution. So let's look at your homework. So I add homework in my course view. That is like a Jupyter Notebook. So if you open it, you get something like this. So this is just like a visualization of what's going on in a convolution neural network. So you have filter one. Filter one has 3 channels and a bias. Filter one has 3 channels and a bias. Filter two has 3 channels and a bias. And notice how like, oh, it's taking the input and outputting it here. Right? Outputting it here, changing the filter, right? Outputting. So this is a pad of 1, right? Pad of 1, and a stride of 2, right? A stride of 2. And in Python, you can write like, oh, simple things like, oh, okay, let's convolve an input, right? Input like this. And let's convolve with this thing. I mean, this thing convolve with 1, 1, 1, 1. Right? Convolve with 1, 1, 1, 1. So the first number is 1 plus 2 plus 5 plus 6, which is 14. Right? So that's you can write in PyTorch, you can write simple pretty much like a simple calculator here. Okay, so let's do some model building. So here is an example of like a project we did 10 years ago with like the Railway Authority of Thailand. Anyone know what this is? It's related to trains. So this is the railway. So this is like the iron railings, the long strip. And so you have this. So usually you have in a railroad, right? In a railroad, you have the parallel lines, right? And you have the board, right? And you have like some clip that fixate the board to the tracks. Right? So you're looking at this small image here. Right? This small image here is the image. So in this image, the clip that is like attaching the board is already gone. Right? This one is still intact. Right? This one is still intact. So this is the goal of like the railroad company, right? They want to do maintenance of the railway, right? Usually they will have humans walk along the railroad, right? Takes a long time, right? Walk along the railroad and then mark the places that you need to fix, right? So this is how they do maintenance. So that is very time consuming. So what they do is, okay, there's a railway, right? We're going to have like a train that move along the railway, and we're going to fix a camera, and the camera just shoot downwards along the tracks, right? So this is how you get this image, right? So instead of like having a person walk, we're going to put a camera on the train and let it run. The train has some GPS that can mark like, oh, okay, this location is missing, this location is okay. Right, so we're going to build a model that look at an image and tell whether there's a creep or there's no creep. Right, so it's a simple binary classification. So what we're going to build is a convolution neural network, which is we take in an input of 224 to by 224, pass to convolution, pooling, convolution, pooling, convolution, pooling. And at the end, we have some fully connect. Right, so let's look at the code. So you have convolution. 3 here is input channel. 64 is output filters, right? How many filters? So we have 64 filters. The input is RGB image. So it's 3 numbers, right? Kernel size is 3. If we only say 3, it means 3 by 3. If we say like, if we want to like, oh, 3 by 5, we do this. If we say only 3 here, it means 3 by 3. It's a square if you only put in one number. Stride and padding. And then there's pool of size 2, stride 2. So we have a bunch of convolution and a basic neuron here, right? A basic neuron here. We need to specify the input. So we need to calculate the size of the layer, right? So here, convolution 1, output of convolution 1 is we have 220. We have also 220 out. When we have pooling, we get 112 because the pooling is stride 2. Okay. Pooling again, 56. Pooling again, 28, 14, 7. And at this point here, how many channels are there? So this 7 by 7 here has 522 channels. So the input to my linear layer here is 512 by 7 by 7 by 7. And let's say, oh, okay, let's have 4,000 neurons out and 4,000 neuron in and 2 class as output. So my model will look like this. Input ReLU pooling convolution ReLU pooling convolution ReLU pooling, right? At this point we have 512 by 7 by 7. We need a command that turn an image into a vector, because the linear layer only accepts vectors input. So we use this command. This command just turn the image into a vector, and then we put in FC6 and FC7 to get the output. Then we say, okay, let's set the loss. The loss is cross entropy loss. Notice one thing. There's no softmax in here, right? I said like, oh, when you use cross entropy, you need to use softmax, right? Where's the softmax here? So in PyTorch, if you use cross entropy loss, if you use cross entropy loss, here is the input is expected to be unnormalized logits. That is like, oh, you don't need to use softmax. This function, this cross entropy loss, will compute it for you. So you don't need to apply it. And the rest is the same. Adam, reduce learning rate on Plato, some data loader, and then train. Right? After you train, you get something like this. That is, oh, in the case where the crypt is missing, you have 20 out of 180. 180, that is wrong. I mean, 180 total, you get it wrong 20 times. Right? So you have like around a 10% error. Do you think this is acceptable for the railroad company? I don't know, maybe, but probably not. You're probably not so happy if you know like, oh, 10% of your missing trips are not fixed. Right. So what do we do? Right? What do we do to improve this? And we'll talk more about this in the second half of this lecture. Another layer that people use, this is usually for text. And this is for text or categorical features. Okay. So this layer called embedding. So what's embedding? Well, let's talk about like what people usually do in categorical features. So let's say, oh, if you have a categorical feature, for example, like day of the week, like Monday, Tuesday, like Wednesday, blah blah blah, until like Sunday, right? How do you turn this into an input feature? You turn this into one hot vector, right? So this is something we use quite typically in machine learning. Turn a categorical features into just one hot vector. This is also called a sparse representation. That is like, oh, most of your input will be 0, right? And you have like a 1 at the location that represent that value, right? So that's one hot encoding. So this is quite wasteful, right? This is quite wasteful. So another way that you can do is that, okay, let's define some mapping, right? Define some mapping from this one hot categories into some numbers, and hopefully this number will represent something according to like what you input. So now these numbers are no longer like sparse, right? We call it a dense representation. And this is usually just a lookup table. They say, oh, apple is this number. Bird is this number. Cat is this number. Right? It's a lookup table. And this are learnable weights. Right? So this number, what we want to represent it as, you're just going to learn. Right? For example, let's say that I want to do a sentiment analysis task. That is, oh, I'm going to input a sentence and output whether this sentence is positive or negative sentiment for the text. So I might have like a fully connected layers, right? But how do I represent text, right? So maybe I have like each word gets a unique index, right? So the word cats always map to 4, right? Cats are always mapped to 4, and every words are unique. So this is like one hot representation, right? But in neural network, we can add an embedding layer, which turn a one hot into dense representation. So notice the same thing. Cats, same number, but instead of one hot, it becomes some value. Right, so this is an example of like a embedding of like words. So let's do TSNE. Wait a little bit. Okay, good enough, I think. So the words here represents the embedding value, right? So you notice like BIOS and DOS and HP and mainframe, Mac, right? These are all computer related words. They are all bunched together, right? So the values in the embedding carry some meaning. Maybe another region like here, enzyme, receptor, fermentation, membrane. So these are all biology terms, right? So the embedding learns like the meaning of the words and turn it into some number. So this embedding technique, right, is very similar in concept to PCA. That is, we're going to turn some high dimensional vector, like one hot or an image, right, into some smaller dimension, right? But the difference is PCA is usually unsupervised, while the embedding can be either supervised or unsupervised, depending how you train it. But the main strength of embedding is it can be nonlinear. Right? It can be nonlinear, so it can be more powerful than PCA, which is a linear projection. So let's do a quick recap, right, of what are the pieces we learned so far, right? We learned about dense or fully connected layers, which are the basic building block of a neural network, right? We have the softmax layer, which uh, turn the output into probabilities. We have the nonlinearity, right, which adds the nonlinearity in the neural network. We have CNN and pooling, which is used in convolution neural network. We have the embedding layer for categorical features. Dropout, right, which reduce the overfitting of your model, right? Or batch norm, which makes your model trains faster and also reduce overfitting. So these are the layers, right? These are the layers. And with these pieces, you can start building something more interesting. So you can treat all of these layers as Lego building blocks that you can just, okay, let's build something, put things together, and it turns into, I don't know, a castle or a building, right? This is what we call in deep learning architectures. Just like a building, right? We call, okay, a building has like floors, right? Different layers, different floors. The same thing, right? Deep learning, we also have deep learning architectures. So let's, before we start this topic, let's do a quick break. Let's 7 minutes, right? 35, the short one, before we go to the next part. let's continue. So let's try to build some buildings, right? Some architectures. So we're going to talk about like pretty much two main architectures that are still commonly used nowadays, or at least like heavily inspired, like recent architectures nowadays, right? Which is LesNet, which is a convolution based, and a transformer, which is a attention based model. So in LesNet, right, we're going to look at one competition which is called an ImageNet competition. So this competition works on a data set called ImageNet, right? So ImageNet has 1 million images and 1,000 classes, right? So these are like some example of ImageNet, right? So you have like leopard, mushroom, grill, right? Whatever, right? 1,000 classes. And this competition is like conducted yearly, right? During the years of 2012 to 2015, right? And actually, like a lot of the deep learning techniques are developed on ImageNet data, especially for images, right? So let's look at the winners of this competition throughout the years, right? So maybe we can understand more and like what are the best practices in building an architecture. So before we go into ImageNet, let's talk about this model called LearnNet. So LearnNet is done by Jon LeCun, who was the chief scientist at Facebook. He quit last year, and now he's running some startup about AI. But this is during his when he was young. This is almost 30 years ago, right? Almost 30 years ago, during his PhD years. So he built this convolution neural network, right? The first well-known convolution neural networks, where okay, there's like convolution, subsampling, and some fully connected. So this is 1, 2, 3, 4, 5 layers. 5 layers. And it's only limited to 5 because during that time there's no GPU, right? There are no GPUs. So compute is expensive, so he can only build small models. Then in 2012, the first winner of ImageNet is called AlexNet. Alex is from the name of the inventor, and he used 2 GPUs, right? One 580, which is 3 gigabytes of VRAM, which is even like smaller than your cell phone. It's very pathetic, right? This so and it's the same, right? Convolution, max pool. There's this thing that is the image looks to be split into 2 parts. because this is GPU1, GPU2. So he draw it into like two parts, but actually it's just convolution pooling, right? But the GPU is too small. So that's AlexNet, right? And notice at that time, people don't know quite well about how to build this model. So that okay, let's use 11 by 11 here. Let's use 5 by 5 here, 3 by 3 here, maybe 128 channels, right? So very random, right? Very random numbers, right? And so this is AlexNet, right? And coming back here, so the next year winner, CFNet. CFNet just pick better filter size. That is like, oh, they tune the model, right? Oh, instead of 7 by 7, let's do 9 by 9. This layer has 50 channels. Let's increase it to 100, right? So notice the size is the same, right? The improvement is around 3%. So you get 3% improvement by tweaking, right? By tweaking. So that's the moral of the story. That is like, oh, okay, you can get some gain. You can get some gain by tweaking your model, right? But it will be quite small compared to what's possible, right? What's possible, you can go even farther, right? If you build the model in a better, using better tools or using better techniques. So another popular architecture is called VGG. So VGG is like the name of a research lab at Cambridge. And they use the name of the lab as the name of the model. This model is popular because it's the first open source model out there. So it's very popular. But if you notice in this 2014, right? The winner is what? GoogleNet. But GoogleNet is not open source. But it's the winner. But VGG is more popular because they are open source, but they didn't win. So we're going to discuss this one because I think it points out a very interesting design choice that is here. Notice they always use 3 by 3. Right? They always use 3 by 3. So instead of trying to like, oh, think about like, oh, this one maybe 7 by 7, this one 5 by 5, right? Just all use 3 by 3. Why? Why? Because we discussed a little bit before that if you have a 3 by 3 on the second layer, a 3 by 3 on the second layer, it sees a 5 by 5, right? So higher layers can cover for higher for larger filters, right? So you don't need large filters at all. You just need to stack them, right? That's why in VGG they stack for 16 layers. So this is the convolution part, and they have three fully connected layers. So people call it VGG 19. So there are 16 convolution and 3 fully connected. And why do we prefer a 3 by 3? So if we have a 5 by 5 filter, how many parameters are there? 25, right? 25 parameters. If I have a 3 by 3 and I have two of them, I stack them into two layers. How many parameters I need? I need 18 parameters, right? So instead of building large filter, you're more efficient if you do two small ones, right? That's why VGG build the model this way, right? It's a better way to get the same functionality but with smaller size, right? So that's VGG, right? And what about 2015, right? What's the main difference between previous and 2015 is the number of layers, right? In 2015 is 150, right? Why did LessNet do such a high amount of layers? So previously, right, people try to build deeper models, right? It's always very desirable to build deeper models, but it's very hard to build a deep model. So what LessNet did is they figure out the trick to construct deeper models. So they can do 150 layers, and they can do it by, so a typical VGG might look like this, right? Convolution. So that's a typical VGG. In LessNet, they add this thing, right? So this is called skip connections, or some people call it residual connections, that just skip computation, right? And this skipping of the computation lets you do gradient descent more efficiently. So this helps the problem of vanishing gradients when you do the computation of the gradients. And nowadays, like all deep learning model pretty much incorporate this skip connection in some form. And then another so that's the end of like this competition, right? After 2015, they stopped the competition because like LessNet already beat human. So like, oh, okay, let's move on to harder tasks, right? But ImageNet is still a very important benchmark in computer vision, and newer models are still developed based on this data set. But the focus are more on smaller models. The model are good enough. By good, I mean enough accuracy, right? But to get the adoption, you need smaller models, cheaper models, right? So that's the goal of like current image models. Another model that people have been exploring is called the transformer. So the transformer is from this paper, Attention is All You Need, right? And this paper just say, okay, we just use attention mechanism, which we'll discuss next, but I just put it here first for completeness that, okay, transformer is another kind of architecture that people use quite a lot. All right, so currently, people don't actually come up with new architectures that often, right? You can think of like just building buildings in real life, right? In real life, you can choose to build a standard house, right? A standard house probably will cost you less amount of money to build compared to like, oh, let's try to build something very sophisticated, like I don't know, like maybe One Bangkok. Like One Bangkok has like very interesting or maybe like very confusing structure, right? If you go into One Bangkok, there's like very strange design, right? And it probably costs a lot of money to design, costs a lot of money to build as well, because a lot of the things are not standard, right? So nowadays, people don't come up with their own architecture. They just use standard ones. Like, oh, okay, let's use LesNet. Let's use transformer, right? Just use standard ones. But they will use it in a different way. That is, they will use it with transfer learning. So what is transfer learning? So, well, if I ask you this, right? Oh, have you seen this? I don't know, thing, this thing before? Obviously no. But can you guess, like whether it's a land or sea animal? Right? It's a space animal. Yes, space octopus. Uh, but yeah, you kind of guess, right? Maybe because like, oh, it's some transparent thing. Yeah, even if you remove the ocean in the background, I can crop it. I can crop it to just this. Actually, this is a lot harder, but but yeah, maybe you see some blue thing and they say, okay, this is probably a sea animal, right? So humans, right, can guess, right, this kind of things, right? Because even though we never seen this before, right, we know some knowledge from past experience, right? So in order to build like uh, a smart AI, right? A smart AI, you need an AI that can learn from the past, right? So how can we do this, right? How can we make the AI learn from past experience, right? So that's where this technique, transfer learning, comes in, right? So there's always a myth that says that, oh, you need a lot of data, like millions of data to build a good deep learning, right? But actually, with transfer learning, you can transfer, right? You can make use of old knowledge for your new data. How do you do this? So let's look at this example, right? So let's say you train a model, right? You train a model on ImageNet, right? You have 1,000 classes at the output, and you have a lot of convolution layers, right? Convolution. Let's say this is VGG 19, right? You train, right? You train using gradient descent, right? And you want to use it on a new data set, let's say flowers data set, right? So ImageNet has 1 million example. This one has 1,000 example. So you're going to say, okay, let's take the weights, like whatever weights here, like, oh, weights here is 0.9, this weight is 1.5. You take this as the start. And maybe since the target label, you might have like 10 labels here. You remove some old parts. This is new. You add in new things for certain part that you require new things. You can think about like, oh, you have some brain. And you chop off certain parts and you plug in new things and you put this brain on a new task. Right? So how do you do this? Right? Let's look at the code. So coming back to our railroad example, right? So here is the error that we got, right? The error is here, right? It predict like this one. It predict no crypt. But actually there's a crypt because there's like this thing here is hiding behind the rock. Right. So actually our model is quite good, but it's not good enough, right? Why? Because our training data 1,000 image too small, right? So what we're going to do is we're going to take pre-trained models or model that people already trained on large data, right? Train on large data. Take it, chop off some parts, and add new things and train, right? So in PyTorch, they have some starting models that you can pick. So this is if you click on this link, you go to PyTorch website, which has a bunch of models that you can shopping, right? That you can do some shopping like LexNet, LesNet, right? VGG and other things, newer models. So usually, and they even have like a comparison list. So like there's a accuracy at 1 that is, oh, in ImageNet, you have 1,000 class. You can only answer one answer. Are you correct or not? Right. Accuracy at 5 mean that, oh, instead of answering one answer, you can answer 5. If any of them is correct, you're good, right? So notice accuracy at 5 is always higher than accuracy at 1, right? And this is the number of parameters. GFlops is, do you know what GFlop is? Gigaflops. Flop is floating point. operations per second. So it measures if you run this model on an image, how much compute you're going to require in giga floating point operation. So it means, if you run AlexNet, you need 700 operations, 700 million operations, like multiply, add, right? Those are operations. So you can shopping from this list. And this page has other things as well. For example, semantic segmentation. That is, tell me which part of the image is a car, which part of the image is the road, which part of the image is like a tree. Right. So we're going to take LesNet 34. LesNet 34 with pre-train equals true. It means, we're going to take the brain. We're going to take the brain. Right. If you set it to false, you only get the blueprint. Right. You get the blueprint, but not everything inside. Right. So we're going to take everything. And we're going to do some surgery. That is, we're going to replace. Right. So ImageNet, the top softmax layer, the top softmax has 1,000 classes. Right. So we're going to replace it. Just like here in the code before, right? The code before we have FC6, right? So we say, okay, let's replace this FC6 with something else. So I say, okay, my pre-trained model in the FC layer, turn it into a new thing that output 2, because it's a binary classification. And what is this number from? It's the size of the LesNet 34 output. So you have to check. You have to go check, like, what's the size, and you put it here. And then everything is the same, right? And if you train it, you will get only 10 error. Before it's 20 error on this non-crypt case. So you went from 10% error to 5%. So in the homework, try doing this on dog breed classification. Right? Copy paste the code and change some variables, right? Point to the correct data and things like that. Right? This one should be very simple, a very simple homework. So to recap the benefits of transfer learning, it will give you a better starting point, a faster training, so your performance go up faster, and you end up at a better place. Right? So that's the benefits of transfer learning. So typically, people don't train their own model from scratch anymore. They will just go shopping from this list or go look at papers. Which paper is open source? You just steal their model, change something, and train on your new data. All right, so that's the first slide. And if you go to the second slide, all right, this slide I just grabbed from Ajahn Pirapon with some modifications. I'm not sure if he used this slide before. I don't know, in your data science. But we're going to talk about this paper on like what's the transformer model. So the transformer model in the paper is a model that translates from some language to another, right? So here is translate from I think it's French, maybe, probably French, and output English, right? So how does it look, right? So this is the transformer model. So it has two parts. One is the encoder, the other one is the decoder. So this part takes the encoder, takes the input, the decoder produce the output. Right, so the inputs go here at the encoder, the output comes out from the decoder. And the encoder is a bunch of layers that people usually describe in blocks. So this is a block transformer block. And we repeat this n times. So in the paper, n equals 6. So you repeat it n times, 6 times. On the decoder, you also have a block that you repeat 6 times as well. So if you look here, right, the layer has a block has two main parts. One is this part, and the other one is this part. Right, a layer has two main parts. So let's look at each of them carefully. So the first is attention, which is something new. So we'll discuss more about this. The other one is feed forward, right? So it's a dense, fully connected layer. So we're going to start with the input, right? The input. So we're going to take in some sentence that we want to translate. So let's say, oh, I put in thinking machines as my input. I will turn it into a vector using word embeddings. So I turn a word into a vector, a word into a vector. And I pass it to some layer, and I get an embedding for each word. So one word has a vector, pass it through some layer, get another vector. Pass it to another layer, get another vector. So as you go along the transformer model, right, the same vector gets manipulated, right, gets manipulated until you get the output, right? You can think of it as like you're trying to transform your sentence into the output sentence, right? So you're transforming this vector, transform, as it passes through the layers. So let's look at this layer, self-attention, because it's a new thing that we haven't talked about before. So this attention layer uses what people call scale dot product attention. So what is this? So let's say that if I have so this is a normal neuron, right? A normal neuron. I have some inputs, right? And I want to predict whether this is positive or negative, positive sentiment or negative sentiment. My neuron might say, okay, I want to focus on the last word. So the last word has like a plus 2. This one is like a plus 0.2, and this one is a plus 0.6. This one is a negative 0.2, let's say. So I have the neuron has some weights, right? The neuron has some weights that combine all the input into an output, right? And this weight is fixed. So if I change the sentence, right? Now the word happy is here. My weights are still the same, right? So my neuron computation is fixed. I cannot adapt to like different kind of input easily, right? So I need a spatial layer. I need a spatial layer that can adapt to the input, right? Different kind of input will have different weights. How do I do this? So the idea of attention layer is okay. It's still a neuron. It's still a neuron. But when you combine them, you're going to combine it with weights that depend on the input, right? So how you're going to do is that, okay, you're going to take the input, pass it to something, get weights, right? And this weight is just a probability, some probability, right? And you're going to use this probability as the number to combine the input, right? So you can think of it as like a neuron that changes depending on the input. This thing here, we call it attention weights, right? We call it attention because, oh, this model is picking which input to focus on, right? To pay attention, right? So it picks what input is nice and put weights there. Right, so this is the big picture. I think it's important to just understand like the basic intuition. Like we're going to have some weights that is something that sum to one to combine the input, right? And we're going to pick inputs that is important for us. And the equation is very strange. So this is the attention layer. So we have Q, K, V. So this is called QKV attention, or people call it scale dot product attention, because here is a dot product actually, but it's not apparent here, but this is a dot product, and it's scaled by the square root d, where the d here is the size of the hidden layer. So in this case, the size is 4. So my input is 2 words, and hidden layer is 4 hidden. So this is my input. I'm going to turn my input into the QKV. I'm going to turn this into QKV by multiplying some weights. So this is the weights of attention layer. Right, so these are all weights. We have three sets of weights, one for Q, one for K, one for V. Each of them has a different weight. You can think of this as like, oh, we're going to change X into 3 different functions. Q stands for query. K stands for key. V stands for value. Right. So what does this do? So let's look at an example. Right. I think I have it here. Actually, no. Let's look at, in my lecture notes, I have some example. Boop, 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 boop. Here. Okay, so each of these like QKV are just matrices, right, that we get from the X, right? We transform it into some matrix, and we're going to compute scores. That is like we're going to do a dot product between the 2 matrices to get some score, right? To get some score. These scores is going to be scaled by D, which in this case has 2 dimensions. Right, so we just go scale it like this, and we pass it to softmax. That is, we turn this into probabilities. This probability is used to select, right? To select which input to use. So I have input 1 and input 2, right? Which is input 1 is 2, 3, input 2 is 4, 5, right? So it selects the first one and selects the second one and combine them into the final output. Right, so this is the computation of the attention layer. But what does this mean, right? My point of showing that that equation is that, okay, you can go look at that equation on your own. But I think the most important thing about this is getting some intuition of what an attention layer do. The reason why we call it query, key, and value is that, well, have you guys learned database yet? But you wrote like Python, like dictionary you wrote before, right? A dictionary in coding, right? So what does a dictionary contain? You have a key, right? And you have a value, right? So the key points to the value, right? So each key points to its own value, right? So key 1 points to value 1, key 2 points to value 2, key 3 points to value 3. A query is the thing that you used to ask, like, oh, I want to know about this. Can you tell me? What do? You're going to like, oh, say, okay, I have a query. I'm going to like, okay, which one is my key? I use the key to match the query, and I say, okay, this is the best key for the query, and I'm going to select value this value as my answer. Right. So just like my motivation before, right? I talk about, oh, you have multiple inputs, right? You have multiple key and values. Which key, which input should I take? I use a query to select. Right? I use a query to determine these numbers. This means, oh, okay, I use 80% from this key. I use 10% from this key. So look at how the interaction is done. You dot product between query and key. You use the query to search for the key. And then you do softmax to turn it into probability. And then you use the probability to select the value out. Right. So that's the intuition. Understanding the math. I think you can go back home and look at the lecture notes and work on the numbers, right? But I think the intuition is what matters more, right? The key and query is used to select each other, right? Do the softmax to get a probability out, and use the probability value to pick out the value. So in the transformer, there are two methods to construct the key, query, and value. You can use self-attention. That is, oh, everything, every X, you use the same thing, same input. That's why we call it self. That is, oh, you use everything from the same input. Key, query, value is computed from X. Another version is called cross attention. You use query from one part of the model, key and value from another part of the model. Because the key and value are usually the same thing, right? You have a dick, right? You have a dick, right? But where do you get the key depending on which thing do you want to select? So for example, if we go back to here, notice how it's split into three parts, right? So this is the query, key, and value. So the three prong here is the query, key, value. And here on this part, so this is self attention. Here you have key and value from the encoder and query from the decoder. Why? Encoder takes what? Encoder puts in the original input, right? Let's say French sentence. So it passed the information. Where is the information located? In key and value. So it passed the information. And the query just say, oh, okay, now I want to translate it into English. Query is the thing that we say, oh, I want this. Right? I want this. Give me the information. Right? So the information is come from the encoder. The query comes from the decoder. I want this, give me information. Right? Key and value contains the information that I want to extract. Another piece is in my calculation of the attention weights, right? I can calculate it like this, right? Into some numbers, right? Sometimes I want to remove certain inputs. Sometimes I want to remove certain inputs. So maybe I can remove this thing. Right? I want to remove this thing. This is called masking. Just removing certain inputs out. Right? This is called masking. So this is called mask and blah blah blah. Like you can do mask self attention, mask cross attention. You can do masking anywhere, right? And in transformer, in the paper at least, masking is done to prevent the model from seeing the future. We'll talk more about this next time. So you don't have to worry about this thing just yet. We'll talk more about this next time. But in masking, what we do is that, okay, when we compute, right, we have X, right? We have X. We turn it into embedding for each word. For each word, we turn into embedding. Each embedding is turned into query key value, and I can do the dot product. Divide by the vector, the scaling, and compute the softmax, right? So this is the typical calculation. But if I want to mask, if I want to mask, I can remove certain parts, turn it into minus infinity, and with the minus infinity, I will get like a zero probability. So this is an example of like masking. Another piece of the attention is called multi-head attention. So basically, when we do attention, we turn X into Q, K, and V. Right? We can turn this into multiple versions. Turn this into multiple versions and do each of them do attention. Do each of them, and then combine them, right? Concat. So let's look at an example. So you have an input, two words for hidden dimension. You have attention head number 1, well, number 0, and attention head number 1. You have different QKV. So you multiply X with Q, get this. Wait, no. You have different weights. So you multiply X with W, get Q. Multiply X with W, get K. Multiply X with W, get V. The other head, do the same thing. Now you get 2 sets of QKV. You do attention on this, attention on this, attention on this, get the output. The output is the same dimension, 2 words, and 3 dimension, just like in the value. The value has 3 dimension. You get 3 dimension out. You have multiple the attention head. Each of them is 2 by 3, 2 by 3, 2 by 3, 2 by 3. So you concatenate them to a big one. So you have 2 by 8 by 3. You concatenate, you get this. In the end, you want to turn this into the same size as you start with. What do you start with? You start with 2 by 4. Right? You start with 2 by 4. Here, you start with 2 by 4. So you want to turn from 2 by 24 to 2 by 4. How do you do this? You multiply by another weight. So you multiply this, which is 24 by 4, which will give you a 2 by 4. Right? So all this thing is just to manipulate your vector, your embedding, combining different vectors into a new vector. Like keep transforming your vector into a more complete version. All right, to summarize, you have an input sentence. You embed them, right? You split into heads, multiply each weights, gets the Q, KV, compute the attention, concatenate them, multiply with a projection, and get the same output size. But the vector is already manipulated to contain the information you want. In this image, right, there's another part that we haven't talked, well, we just talked about this. Multi-head attention. This is what? This add thing. Add is residual connection from LessNet. Norm. This is layer norm. Feed forward. Add and norm is also residual plus layer norm. So the only piece we don't know yet is this positional encoding. We know this embedding, we know already. So we're only missing this piece, positional encoding. So what is this? Oops. So let's say I feed in this image. Not image, this sentence. The black cat fights the white cat. So I turn this into a vector. I turn this into a vector, 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 vector through embedding model, right? To the embedding layer. The two cats here is the same word, right? It's the same word. So I will have the same vector here. I will have the same vector here. And I will pass these two vectors through attention layers. Right. The problem is if I pass this two vector to attention, I will get the same, let's say pass to attention, I will get the same vector out. I mean, not, it will be a different vector, but the two words will have the same vector because attention layer is commutative. That is like you can switch the order of the words as long as it's the same vector, you will get the same number because attention is what? Multiply and add, and softmax. All of them, you can swap order and you get the same number. So we need something to differentiate these two cats because we want them to be slightly different, right? Because this one is a black cat, right? This one is a white cat, right? They are different. All right, so how do we do this? This is where this thing come in, positional encoding. we're going to put in position information to the word, right? So we're going to add like, oh, let's add something to this thing, and each vector will be slightly different. Right. So these two cats will ultimately be slightly different as well. So what the paper did, which is not the best, but what they did. So we're going to talk about what they did. They say, okay, we're going to create these two equations, which is very random actually. So don't think too much about it. Don't think too much about it. I mean, sometimes you just do things, right? Especially like in the early days, right? Oh, okay, let's try this. Oh, it works. Happy, right? So they just, okay, let's do this. Well, one thing to discuss about this is sine and cosine. What's good about sine and cosine? It's limited, right, to 1 and minus 1. So that's a good thing. One good thing that, oh, that's why they pick sine and cosine, so that this number is limited, right? And what is this? Usually, like in a sine, is like what? Some angle, right? And the sine repeats when it's full 360 degree, right? So this number is just to make sure that when you calculate these vectors, it won't come back into a circle. So you pick a very large number here so that your angle won't come back. Your angle won't come back at the start, so that your number will always be unique in this 10,000. Right. So don't worry too much about like these exact things, but that's the main idea. Like, oh, you want something that is limited, and you want them to all be unique. Right? You want all of them to be unique. So if you plot this, notice how there are two positions. So this is position of word. The first word, the second word, the third word. This is dimension of embedding. So let's say that in my thinking machine, right, 2x4, this is pose, and this is I. Right, this is I dimension. This is pose dimension, like thinking machines. So I have a even function and an odd function. So I have like even, odd, even, odd, even, odd, even, odd. And if I plot them, I can plot into position. So this is the pose, and this is the I. Notice each vector, you want each position to be unique, right? You want each position to be unique. So each vector here is unique. The entire vector, not certain values, but the entire vector. If you compare them, they are all unique, right? That's the only specification we want. right? You want, okay, all of them to be unique. So what we're going to do is, okay, for each word, turn into embedding, compute that equation that we just did, add them. That's it, right? That's it. This is all just for so that the same word will be slightly different at different position. And like I said, don't worry too much about what the transformer paper did because it's very old by now. It's like 10 years, 11 years old. Nowadays, there are other techniques. So in the transformer paper, they did what people now call absolute position encoding. That is, oh, you know the position, you can calculate the value. Is the 10 word, you can calculate that. Is the 15 word, you can calculate that. You just know the position. So it can be fixed. For example, the sine and cos. This is the original transformer. It can be learned. That is, oh, why not gradient descent? Why not gradient descent to learn what the number should be? This is what done in GPT, which is ChatGPT pretty much. The early form of ChatGPT use this. Nowadays they don't use this anymore. Nowadays people use this one, relative position encoding. Or people usually call it rope. Somehow, I don't know why it's well, actually, yeah, rope stands for rotational position encoding. So this is a kind of relative position encoding that is used pretty much in modern models. They use rope. What is a relative position encoding? Just like the name suggests, you can only calculate the embedding in a relative position. Like, oh, okay, this cat and white, right? And there's a black and cat. These two words are next to each other. These two words are next to each other. They have the same position encoding relatively. Right? It's calculated in a relative manner. And Leonore, we did this. All right, so that's it. In the end, we have some input, right? We calculate self-attention and pass information to the outputs, do some embedding as well, and in the end, you have a softmax to predict the word. Right? That's the attention. I mean the transformer model. Right? So in the end, you're like, okay, compute some probability of the word. Right? And there's like very strange words in here. But yeah, so you compute like a big softmax layer. All right, that's it for today. If you have questions, feel free to ask now or whatever offline. or as the AI tutor. uh, I think AI tutor is very useful in these kind of things. You just ask it to spit out like examples, calculation, or whatever, or explain like details. Uh, oh, and you might notice like the question asked in the Discord, I messed up a little bit in the scheduling. Next class is the last one we have. So there will only be one more quiz, right? And the last one will be just extra points for you guys.